Today, it's not so much about math as it is about understanding the context in which we work. So today, I want to talk about hardware, maybe something that is not so common at the MVA. Explain to you what are the main trade-offs with GPU programming. And so today's session maybe is going to be to look a bit technical for you. If you've never done any kind of low-level programming, like if you've never done any C++, but don't worry, okay? The main message here is not that it's important and you should remember everything. It doesn't count for the exam anyway. It's just there to show you, everything that's under the hood and that allows us to work efficiently as researchers. So, this slide of intro, I've used it 2-3 times already. You remember that the main motivation for this lecture on geometric data analysis is that the trend over the last few years have been to work towards a continuous analysis of large data sets. The idea is that now that we live in the big data era, we cannot really understand our data sets as small, simple graphs anymore, as discrete objects, but that it starts to be more efficient to understand our data sets as manifolds. Either pseudo-manifold, like high-dimensional spaces of images, or as genuine physical manifolds, as in 3D meshes. And so this push towards continuous tools, continuous theories, has motivated, the introduction of the vocabulary of Riemannian geometry that we used 2 weeks ago to describe probability distributions. And so that's probably the work of our generation, to make it easy to work with continuous objects. And as I told you, it's something that physicists have already done, decades ago. So this push from small dynamical systems with maybe a handful of planets in the solar system was then made more complex in the 19th century, with statistical physics. You have the ideal gas model by Boltzmann. And now we are able to describe fluids. And it's one of the main successes of physics that it's possible now to simulate those kind of impressive dynamical systems with an infinite number of degrees of freedom. And now the thing is that at the MVA, we are not only interested in theory, we're also interested in nice simulation, nice results. And so it's very important to understand the computational environment in which this research is done. And the thing about research in physics, since the 1940s, is that it has gone hand to hand with the development of high-performance supercomputers. It's well known that computers were motivated by cryptography, during World War II, and by the needs of simulations, mainly for the atomic bombs. Like the CEA in France, it's directly tied to atomic simulations. The same story in Russia, the same story in the US. So, this is really where computers come from. And historically, those kind of large, high-performance supercomputers, those kind of clusters that physicists use to simulate plasmas, have only been available through large institutional centers. So basically, if you work at the CEA, you have access to the clusters of the CEA. Same thing if you work in Los Alamos. But if you're out of it, like if you're in a hospital, you don't have access to great computers. And basically people have only got access to those computers with like a 10 years or 20 years delay. And so that's why you have kind of a separation between HPC and general purpose programming. And so that's for physics, but the revolution, over the last 20 years has been that a similar shift from discrete to continuous objects has taken place in the industry that focuses on video games and movies. I think we're all more or less from the same generation, born in the 1990s, more or less. And basically, we've seen that with our eyes. Like if I look at kind of video games that we were playing when we were children, Final Fantasy VII on the PlayStation 1, it looked very blocky. Like you had maybe a few, maybe 1,000 vertices to describe a character. And now, 20 years later, it looks continuous. Like it's very impressive, this progress. And all of this, like all of this research in graphics, and I insist that, maybe we take this for granted. We think, oh, it's video games, but there's a whole research field that is dedicated to this. And personally, I really enjoy looking at research papers from the video game and the movie industry, like from Pixar, from A to B. If you want to find them, you just type SIGGRAPH. You type SIGGRAPH in YouTube, you're going to find tons of very in-depth presentation of very advanced algorithms that have made this possible. And so this research in graphics has gone hand-to-hand with the development of graphics processing units, or GPUs. Okay, GPUs, which are dedicated hardware accelerators that today, as you know, we use for AI, we use for general purpose machine learning, but that initially were strongly motivated by 3D graphics. Okay, and so I insist that this is a physical object, and so I don't know if you know this guy. It's Jensen Huang, like the CEO of NVIDIA for the last 20 years. And every year, it's kind of Christmas for grown-ups. He presents the new GPUs, always with a leather jacket, saying, oh, it's going to be incredible. And over the last 20 years, definitely, this company has delivered. Okay? And what's most impressive to me is that unlike HPC clusters that were developed for physics, for defense applications, GPUs are affordable to any researcher. Like entry-level GPUs cost maybe 1,000 euros. So any research lab anywhere can afford it. And this is what makes it a game changer. Basically, GPUs, it's high-performance computing available to anyone, especially to people in hospitals, in other industries. Okay? So it's really the combination of high performance and kind of democratic hardware. So that's what I want to stress, that this AI deep learning revolution that probably motivated you to come and study at the MVA is primarily driven by hardware. Okay, like statistics, machine learning, they have been around for decades. And what is really special about the last decade, the revolution, the breakthrough that happened, 10 years ago, people like to cite this paper from 2012, like AlexNet, but it was really kind of community efforts between 2010 and 2015, is that hacking PlayStations to do science became easy. It was already possible in 2005. You can find some very early papers of people using GPUs to simulate galaxies, this kind of thing, but it was really a niche thing because it was very hard. And 10 years ago, basically, libraries appeared that allowed general scientists to do it, and this is what allowed the field to explode. Okay, so I think that it's important as AI researchers, even if you want to focus on math, even if you want to focus on data, I think it's good to spend 2 hours to understand what is a GPU, okay, and how it constrains the type of model that we can develop. So today, okay, we're basically like 2.5 hours lecture and then short exam. We're going to ask ourselves first a question: what is a GPU? And we're going to see that, okay, basically it's thousands of cores for very cheap. And the main trade-off, the main thing that you have to worry about when you buy a GPU is complex memory management. Like, we're going to understand that scientific programs are not really limited by the amount of computations, but mostly by the amount of memory accesses, memory operations that you make. Yeah, and this is what is hard about GPU computing, is to handle all the different types of memory layers. Then I'm going to show you maybe 4 rules of GPU programming that I think are easy to understand as mathematicians, as engineers, but that hopefully can allow you to understand the main trade-offs here. And then, okay, after a short break, I'm going to talk about the current trends in the semiconductor industry. I think it's important to understand that because we are completely tributary to the progress in this field. So I'm going to talk about just-in-time compilation and custom AI chips, and finally conclude by looking at the supply chain issues that have become very real over the last 3 years and their impact on our careers. Just to let you know that probably the next decade is not going to be anywhere as easy as the previous one. So, just for you to know that this is going to be a very high-level introduction, because I assume that you've never seen a line of code of C++, so or God forbid of assembly. So it's going to be kind of easy, and I think basically this lecture is just about raising your interest about this field. So here I list a few references that I think are accessible for people who have your background. So first, if you want to have a nice textbook, PDF file that you can read, coming like with a typical engineer background, I think you can look at chapter 2 of my PhD thesis, which is probably the main reference for everything I'm going to show today. So geometric data analysis beyond convolutions. You can find it on my website. And to go a bit deeper, you can go at the lectures of the lecture note of Albert Chen, which is a colleague of mine in San Diego, who wrote a really nice textbook on introduction to computer graphics with lots of nice diagrams, etc. So that's for like a mild introduction. Then, if you don't know what to do in the evenings, I advise you to have a quick look at 2 YouTube channels to learn about hardware. So first, Branch Education. It's really awesome visualizations of physical circuits, if you want to understand how those magical devices came to be. And if you want to get some context on the industry, understand all the supply chain issues in Taiwan, etc., maybe you have a look at the Asianometry YouTube channel. It's very interesting. And finally, if you want to do real stuff, if you want to learn how to code on GPU, beyond PyTorch, essentially, there is great software documentation available for NVIDIA devices. Okay, and I really want to insist that you have several hardware manufacturers for GPUs, like you have NVIDIA, ARM, or AMD, Intel. But as a matter of fact, in research, NVIDIA has a complete monopoly. And the reason for that is that NVIDIA has consistently, over the years, invested in hiring top-level scientists, excellent software developers, and having them basically write a good documentation. So even if the hardware that is produced by Intel is comparable to the hardware that is provided by NVIDIA, on the software side, it's not even close. Okay, and so that's why, for me as a researcher, if I want to develop a custom extension for PyTorch, for my application, it's much easier to do it for NVIDIA GPUs. So, for instance, personally, I learned all of this first by looking at the NVIDIA dev blog, like the Mark Harris posts are a great introduction to this, and at the GPU Gems textbooks that are illustrated examples. And if you want to go deeper, everything, and I really mean it, everything, from the precise diagrams to assembly instructions, is online in the CUDA toolkit documentation. And you have great references about, how should you implement a matrix multiply? It's in the CUDA repository. Or how should I implement a sorting algorithm? It's in the CUD GitHub repository. So you can find everything online. And I'm very impressed by all of this documentation. So that's for you to know that if you want, you can go deeper. But today we're going to just skim the surface. So what is a GPU? We're going to start with the marketing that NVIDIA provides to the world. And we're going to see that it focuses on a very simple message, like GPUs, it's CPUs at scale. So first, let's start with a very nice, very funny video from 2009. So remarkable piece of marketing, because 30 years later, we're still watching this.
All right, I introduced to you Leonardo. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes in which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target. Hopefully, when it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
In 10,
9, 8,
7, 6, 5, 4, 3, 2.
Thank you.
The message is that it's just that with a GPU, you buy like 10,000 cores for something like 1,000 euros. And so since a typical CPU contains just 1,000 cores, then you'd expect, since a CPU contains like 10 cores, typically, you'd expect a speed up by 2-3 orders of magnitude. So you have those kind of curves that you can find on the website of NVIDIA, where you have decades, and then in log scale, let's say the typical number of operations that is performed by a device that costs $1,000. And you know that Moore's law, this exponential growth of compute power, corresponds to a linear curve in this log scale. And the message, which is kind of true, okay, we are going to see a final version at the end of the lecture, is that until the early 2000s, it was very true. Like you could noticeably see an improvement in terms of compute capabilities of CPUs, and then it plateaued for hardware reasons, physical reasons. You know, it's not even that important, but that, you know, even if the capability of one single core plateaued at like 1 gigahertz, you know, 1 billion operations per second, the unit costs of one core decreased. And so this is a bargain that NVIDIA offers you. Now that one core costs like $1, I sell you 10,000 cores for $5,000. So you should be happy. Okay, so it's kind of true, but here and even in the video, you can understand if you dive a bit deeper that something was hidden from you. You know, how did we fill those tubes with the correct paintballs? Because saying that once you have filled each tube with the correct paintball, you just have to smash a button and you get a picture is fine. But then the main question is like, how did this information get there? Okay, and it's once you ask yourself this question that you understand why GPU programming is hard. Because most scientific programs, both GPU and both on CPU and GPU, are actually memory bound. Okay, the complexity that we learn at school, where we were just counting the number of additions, multiplications, is not that relevant to modern numerical analysis. Actually, the problem, whenever you write a scientific program now, is how do your cores get the correct values for the input float numbers before actually performing this computation, computing an exponential or whatever. You know, and it's something that you've seen in real life. Okay, it's kind of the curse of parallelism. If you have more than 1,000 workers and you ask them to go at the same location to read some memory from the input arrays, you're going to get traffic jams. And the only way of avoiding this is to sort out your cables. So you need to enforce some structure. And so, you know, basically you need to say, okay, no, to give colors to your cables, decide that some cables go at some locations, etc. And when you make those design decisions, you are biasing your device towards some kind of computational architectures. Like you lose full generality. And obviously, manufacturing, selling a hardware device is expensive. So in practice, engineers at NVIDIA have to make design choices to favor what they believe are bankable program architectures that are going to be worthwhile. Okay, and over the last 20 years, a very bankable application was 3D graphics. Okay, so now that we're all hacking PlayStations, we have to understand like do our scientific computations look like 3D rendering computations or not? And that's what we are going to see today. So let's open a GPU, like typical GPU that I used during my PhD thesis, an RTX 2080. And if you open this and remove all the clutter, basically you see this kind of chip. So this is really the core chip on a GPU that contains like 7,000 cores here on this GPU. And okay, maybe this is a silicon chip, but you can go on NVIDIA website and they show you a very nice diagram, okay, that we are going to inspect in detail at the end of the lecture. And the first thing that you can remark is that this organization, this floor plan, looks exactly like the plan that you find in large departments, in ministries that were designed in the 19th century. Basically, this picture looks exactly like this plan from the Admiralty and War Offices that was designed in the 1880s in London. So what you see essentially on those plans is that first you have one big library where where mail arrives, where information is exchanged with the outside world. And then basically most of the space is taken up by redundant blocks, maybe 100 redundant blocks on a typical GPU. And if you zoom inside of those bureaus, inside of those redundant blocks that are called CUDA block on a GPU, this is a picture that you see. First, you have some workers. On a typical GPU, it's like 100 workers that work in parallel from each other, and some memory buffers. Because the idea is that if every time workers wanted to access information, they needed to get up, go in the library, and then come back to their office table, you would get traffic jams. So in order to avoid this, the architects allocated room, storage place, first for some draft paper that are allocated to each worker individually, and then to a kind of office shelf that is shared by all the members of a single group. Okay, so in CUDA, in the GPU world, basically the big library that is shared by the whole device is called the device memory or the device RAM. Okay, so when you say that, oh, my GPU has 16 gigabyte memory, you're talking about the size of this big library. And then you have, in reality, a bit more than that, but you have at least two intermediate memory buffers. So one shared memory that allows different workers to exchange information, and then a register, so a very small sheet of paper that allows each worker to store intermediate computations during the computation of an exponential or whatever, thread memories. So, why are GPUs designed the way they are? First, there's a physical reason to it. I don't know if you ever watched a documentary on the fab labs, on the factories where chips are produced. Okay, it's important because this is a foundation of all our work, and probably you know that all of this is made out of silicon. Okay, so the first step whenever you manufacture a microchip is to grow a silicon crystal. So basically, you have a machine, very specific physical conditions like temperature, pressure. You start from a core, and then it turns on itself. You wait for some time, and you end up with a pure silicon crystal. Like the typical diameter is like 30 centimeters or a bit more. And then you slice this in small disks, and then you place those disks in a machine that is going to etch using photolithography a circuit. So in practice, you know that GPUs are produced by NVIDIA. It's not exactly that. Basically, NVIDIA is a company that that draws the picture that's going to be printed. But the company that actually prints it for NVIDIA, it's called TSMC, and it's in Taiwan. Just so to know, so it's very important. It's very important companies. And so what happens is that the photo that is printed, as you see, contains several copies of the same chip. So here, basically, each of those rectangles corresponds to one chip. Okay. And then, as you can imagine here, we are printing electronic circuits at a nanometer scale. And if you have just one impurity, like one piece of dust or whatever, it's going to create a short circuit. So part of the circuit is going to be non-functional. And as you can imagine, in those fab labs, you have very strong. They make a very big effort of cleaning the air as much as possible, but you can never guarantee that you are going to have zero defects. So it's very important in the design of the chips to have a mechanism in place to have something functional, even if a piece of dirt killed or destroyed some of the circuits. So basically, what happens is that NVIDIA prints a floor plan with something like 128 individual blocks. And then some of the chips are perfect, okay, they're sold at a premium, but most chips have some defects. And so the chips where you have at least 100 offices working, they are sold as GeForce RTX 3090. And then the chips where you have only 80 cores, 80 blocks that are working out of 128, they are marketed as RTX 3080, and then below and below 3070, etc. Okay, and so it's very important to have this redundancy. Otherwise, NVIDIA would have to scrap essentially 95% of all chips that are produced, and so they wouldn't turn a profit. Yes. Yes.
Is it the same difference between i3, i5, and i7?
I don't know. Yes, I assume it's something like that, but I don't know. Yes, but this, it's a common issue for all microchips. Like testing of microchips is also a big topic, obviously. Like, how do you test that the cores work? So that's the first reason. And then the second reason is that GPUs, they are optimized to render 3D meshes in real time. And I don't know if you've taken lectures on that, but today, when we want to render a video game, we actually simulate light rays. Okay, like, it's recent that it's possible to do it in real time, but basically you have a 3D scene, which is encoded as a 3D mesh. And then to render the image on your screen, the computer, so the hardware accelerator, is going to simulate maybe 10 or 100 light rays per pixel. And then for each of those light rays, it's going to simulate how it bounces off. It's going to simulate diffusion. It's going to simulate refraction. And then depending on the number of light sources, you get shadows, etc. Okay. And the objective is to get to those images that rely on pretty simple math, actually. So you can go look on those websites like ray tracing in 1 weekend. It teaches you how to do it. Okay. The miracle is how do you do it in real time? Well, this is where GPU come from. And by the way, when you buy today a gaming GPU, it's called NVIDIA GeForce RTX. The RTX explicitly stands for ray tracing. Okay, so it's explicitly about that. And the idea is that the GPU is going to dispatch the job to the different cores by just cutting the screen into small tiles, okay, independent tiles that work in parallel. And so it's important, to render the 3D scenes, to have this 2D layer of this array of cores, which should all be able to perform geometric computations, like compute Euclidean distances, etc., and to handle textures, like small images, at a very rapid pace. So those are the constraints, that shaped the design of those chips. And now, the end result, as far as we are concerned, as scientists, is that we have access to 5 main layers of memory storage whenever we write a computer program with GPU. So when you buy a GPU, basically you buy 100 blocks of 100 cores, so around 10,000 cores. And you can store data first on a hard drive or on an SSD drive. So maybe you have 1 terabyte of storage space, but obviously it's going to be slow. Like it's not going to be 1 nanosecond of latency to get this. So first you can use a hard drive, or you can use the RAM, the main memory of your computer, like maybe 64 gigabytes, 128, something like that. And then on the GPU device, you have 3 important layers of memory. First, you have the device RAM, the thing that is around 10 gigabytes or maybe 40 if you're rich enough. So this is probably the layer of memory that you're familiar with, because whenever in PyTorch you write send it to CUDA, basically you are asking for a copy operations from the host RAM to the device RAM. So it's an important layer, but you have to keep in mind that this is just a big library, in the Admiralty and War offices. So it's still very far away from the compute cores. Actually, the 2 intermediate layers of memory that are close to the compute units, so the shared memory and the thread-wide registers, are very small. So you don't have access to a few gigabytes per core, you have access to around 1 kilobyte per core. So you have just enough buffer space available to store maybe 100, 200 float numbers, but not much more than that. And so obviously a GPU program is going to spend a lot of time swapping memory between those different buffers. And the main thing you have to keep in mind is that the latency, so the time it takes for a GPU core to get access to the device RAM, is about the time it takes to make 100 arithmetic operations. Okay, so whenever you see an O of n or an O of n square analysis of an algorithm, keep in mind that a memory access costs 100 math operations. Okay, so it's not at all a negligible constants. And so whenever we write real-world algorithms, if we are not just interested in asymptotics, but if you want to get faster in time, you have to minimize the number of times you call those kind of instructions, okay, just because of the way circuits are designed. Now, so if I had to summarize all of this into just 4 rules of GPU programming, I would give you those ones. So first, you want to promote blockwise parallelism. You really don't want your blocks to have to interact with each other. So maybe inside a block, threads can talk to each other, but outside of it, it's going to be very long, because you're going to have, the only way they can talk to each other is through the device RAM. Second, as you know, you want to reduce the number of memory transfers between the GPU and the RAM, or God forbid, between the GPU and the hard drive. So PyTorch gives you some instruction to mitigate this problem. And then if you go deeper, you also want to reduce the number of memory transfers between the shared or the thread memory and the device RAM. And also, you want to avoid making too many random memory accesses. Okay, the idea is that, if you look back, if you come back to our 19th century analogy, if you ask all the workers in an office to go and fetch memory in the big library, it's going to be much more efficient if you just ask them to go and fetch a book from the same shelf. Okay? Like making memory accesses that are contiguous, like reading bytes at locations that are close to each other on the device, is going to be much more efficient than having to make random memory accesses. So GPUs are completely biased towards blockwise contiguous memory accesses, and so you want to avoid randomness as much as possible. So that's for the main rule. Now, Basically, okay. That's the theory. And how does it work in practice? So today is not a lecture about C++, but I think it's important to just demystify this, just show you that those programs were written by someone, probably a scientist, using a syntax which is not that hard. Personally, I'm very impressed by all this CUDA environment, all those, this NVCC, basically this compiler, because using a fairly straightforward extension of C++, NVIDIA allows us to express very efficient programs. Basically, you don't really have to dive into the details of how many cores do I have, etc. The compiler does it for you. Essentially, whenever you write a program in CUDA, you just have to specify the numerical type. You have to say, is it an integer? Is it a float number on 32 bits or 64 bits? And where do you want to store the memory? Like, should it be located in the thread memory, in the shared memory, or in the main device RAM? So that's the syntax. So I'm just going to go through every word, tell you their meaning. So first, like those underscore keywords are the new keywords that are defined by NVIDIA. So global means that this function is going to be parallel code that's going to be executed by the blocks. And we do not return anything. We directly read and write from the memory. So then my CUDA kernel, so my CUDA program, takes 3 parameters as input. So first, an integer, like a parameter. And then, a float star just means the address of an array of float numbers. So here, that's the address in the device RAM of my input data, and then the address of where I want to write, of the output data. And then you have specific keywords like block ID X, block dim X, thread ID X, that allows each worker to know its label. Like, okay, I know that I am in office 29 and I'm worker 36. Okay, so, and if you know this information, you know basically which patch of the image you should render. You know which part of the array you should process. So here you just say, okay, this is my current label. It's an integer number. It's equal to this. And then you can declare variables using very standard C++ syntax. So here I am declaring a new float variable, so a floating point value that's equal to 0. And by default, if there is enough room, it's going to be stored in the thread memory. Then if you want to specify access to the shared memory, you have a keyword, extern shared float. Okay, and this is just to say, okay, this is my pointer to the shared memory. And then you just write standard C++, and implicitly, CUDA understands, okay, in which direction memory flows. So for instance, if I say that some value is equal to device data at location I, like at cell number I want to read device data, then here, some value, it's supposed to be stored in the thread memory. Device data, it's in the device RAM. So this is a memory transfer from the device RAM to the thread memory. Likewise, this is a memory transfer from the device RAM to the shared memory. And then, okay, like once you've understood that, this is just standard C++. So you can just write code, and it's going to be executed in parallel by all the cores on your GPU. So, I mean, you can do stuff. And if you want to explicitly ask for threads in a CUDA block to wait for each other, there is a specific instruction for this, like synchronize the threads. Do that. And that's all you need to understand. Basically, once you've done your computations, you can write it back to the device RAM by using this kind of statement. Okay, you say device output at location I should be equal to some value. And CUDA understands that this is the type of memory transfer that you want to do. Okay, so this is a CUDA kernel. So this is a code that's going to be executed by a block. And then you also have to specify how you want to execute it. on which data. And for this, you write, once again, a standard C++ function like main executed by the CPU, where you're going to define, the size of your data, an integer. You're going to store, to get some pointers to arrays in your memory. So this is just the equivalent of NumPy arrays or PyTorch arrays. And then, you have a very verbose syntax. Okay, that's one of the downsides of the API. It's very verbose, but it works. Where you say, I want to allocate memory on the device. I want to allocate an array which is large enough to store like 1024 float numbers. Then you can copy information from your host RAM to the device RAM. And then you just specify the number of blocks that you want to use, how many workers per block you want to use, and then using the syntax, you execute your CUDA kernel on your input parameters. So verbose, but fairly straightforward. Then you wait for the GPU to finish its computations. And once it's done, you just copy back the results from the device RAM to the host RAM. Then you do whatever you want, you process, you create a nice plot. Then you don't forget to freeze the allocated memory. Otherwise, users are going to get an out-of-memory error. And then you exit, and you're done.
For example, if I have two matrix multiplication to do I have to ask all the workers to first do the first multiplication, then I wait, they finish, and I push the second one? Or could I say, half of the block will work on this and half will work on that? Is it possible to separate those tasks?
Yes. So it's possible to both. The keyword you can type on Google, it's synchronous or asynchronous computations. Okay, so it's simpler, obviously, to do everything synchronously. So first, you perform one matrix multiply, you wait for everything to finish, and then you perform the second matrix multiply. And initially, most libraries were working exclusively in this mode. But then the problem, if you do that, is that you may be a little bit suboptimal. Because maybe, basically, if you introduce too many wait statements, too many synchronized statements, some cores are going to just stay idle while their friends work. So nowadays, over the last 5-6 years, libraries have become more and more complex and done everything that was needed to hide those latencies. So, for instance, PyTorch. This is exactly why, if you want to benchmark the PyTorch code, you should explicitly write torch.cuda.synchronize before your time it statement. Okay, and why? That's because out of the box, PyTorch, basically, you call an operation and immediately it tells you, yeah, it's fine. Because what PyTorch does under the hood is that it adds your operation to a stack or a pile, to a queue of operations that should be performed, and basically gives you back the hand so that, for instance, you can load memory from, you can load data from the hard drive, etc. So essentially, it's possible to do things asynchronously, but it's more complicated. And so, basically, only try to do that if you see that it's really a bottleneck in your code. Otherwise, it's a lot of trouble to handle this, because asynchronous memory accesses mean that maybe you're going to have race conditions. It can be complex, but it can be done. So I don't know if you have the questions. So, okay, all of this to say that it's a bit complex, but not out of reach, and this is what has enabled scientists to work. So if I had to do a recap on GPUs at a high level, I would tell you that, okay, for 1,000 euros, you buy one GPU, so 10,000 cores, or more precisely, 100 blocks of 100 cores with 5 main layers of memory. And the main trade-off is that all the large arrays, everything that can store gigabytes of data, is slow. So a memory access or a memory write costs 2 orders of magnitude more expensive than arithmetic operations. So you would like to use the fast buffers, but they are very small, like only 1 kilobytes per core. So just enough room to store 100, 200, 500 float numbers, which is very limiting if you do image processing, for instance. So now the thing is that if you want to optimize the shared and the thread memories, it's doable, but only in C++ or assembly. So most scientists obviously don't want to do that. Okay, you want to focus on your data, you want to focus on your patients, you want to focus on your models. And this is why most scientists rely on pre-existing libraries of CUDA kernels, which are essentially pre-compiled binaries. So the idea whenever you write a PyTorch program is that basically all the variables that you manipulate are arrays that are stored in the device RAM. And then every operation you call is a binary that is executed, actually that takes as input those arrays. It's a function like this that takes as input the arrays, performs some computation, and then write it back. So out of the box, if you work at the Python level, you cannot avoid making many back and forth between the device RAM and the course, but that's a trade-off. It's already good enough for plenty of applications. So that's why most scientists, most of our colleagues, they never dig deeper than this GPU device RAM. And so most people, I think, are not even aware that you have those thread and shared memories inside that make everything work. So now, just to be clear, I think that we can look at a practical example, which is nearest neighbor search. Okay, nearest neighbor search. Look at different implementations of this operation and see how you can improve things. First, by working with PyTorch on the GPU, then by using the correct binaries, and then maybe by doing some kind of C++ magic. Okay. So by nearest neighbor search, I mean that first I create an array with m rows, think like 10,000 rows, and d columns. So d may be equal to 3 if you're doing 3D stuff. Maybe it's equal to 10, maybe it's equal to 100, maybe it's equal to 1,000. Like for mnis, it's equal to 784. This is the number of pixels in m. Then you have y, also an array with n rows and d columns. And what you're interested in is for each point x, for each row xi, a vector with d features, you want to know the index of the point y, which is closest to xi. So basically, you want to compute the matrix of square distances between the xi's and the yj's, and then perform an argmin reduction. So the way you would write it naively is like this. So x, okay, like random numbers, size md, nd, and then you use, this broadcasting syntax. I hope you're familiar with it, that allows us to express that x minus y. I don't want to compute row-wise differences. I want to compute all pairwise differences between the points x and the points y. So to do this, I add dummy dimensions. So I say that x, understand it as an M1D array, like as a 3D array, understand y as a 1ND array, and then if I write x minus y, Python understand that I want to compute an MND array. Okay? So that's your differences. And then if I want to compute a Euclidean distance, first I have to square all those values, and then take the sum of the number of features. So if I work in 3D, I have 3 terms in my sum. If I'm working in dimension 100, I have 100 terms in the sum. So I get an MN array. So that's my matrix of square distances. And then I perform an argmin reduction, and I get my indices. So that's probably the way it's taught. Standard thing. And how does it perform? Well, fairly poorly. First, because here we haven't used the GPU. Okay, out of the box, torch.ren refers to an array which is stored in the host RAM. So all of this code just happens here between the host RAM and the CPU. On the CPU, you also have intermediate memory layers, but that's the idea. Like everything happens here in this code. And the main bottleneck, well, is going to be caused by these operations. Okay, when I instantiate here the array of differences, this M and D array, wait, I'm allocating a very large array in RAM and I'm filling it using the CPU. So I pay M times N times D CPU operations and memory transfers, and it's going to be very slow. Like beyond M and N that are equal to 1,000 or 5,000, you're going to wait a few seconds. If you want to work with high resolution 3D meshes, it's not going to get it. So what you can do, I think that's what you've learned already, is you can send your arrays to the GPU and use the GPU backend that is provided by PyTorch for all of those operations. So this is typical code. So X underscore, that's my array in RAM. Y underscore is my array in RAM. And then using this point CUDA instruction, I am explicitly asking PyTorch to copy this memory from the host to the device. And then PyTorch automatically understands that all those computations should be performed on the device RAM. And so every single line here in this program corresponds to a binary. First that takes as input X and Y on the device RAM, and then do some kind of dark magic with shared memory, thread memory, GPU cores, and creates an M and D array in the RAM that has all the required values, etc. Now you look at this program, and where is the main bottleneck? Okay, so we are making computations first. Okay, at the very least, this operation is going to require M times N times D GPU operations. Okay, because we have to compute this one way or another. But here's the bottleneck. Is not going to be arithmetic operations, but memory transfers. And why? That's because when I write this equation, this line, I am explicitly allocating a large MND array. I have to fill it. So one way or another, I'm going to have to pay this cost. And remember that every memory access to the device RAM costs 100 arithmetic operations. So it's very expensive. And so this is going to be the bottleneck of this program. So what can we do here? Well, a first option, which is very popular in the machine learning community, is to leverage the fact that the squared Euclidean distance has a nice mathematical form. Basically, you know that the square distance between X and Y, it's equal to the squared Euclidean norm of X plus the squared Euclidean norm of Y minus 2 times the dot product between X and Y. So you can pre-compute ahead of time the Y squared, the norms of the Y's and the norms of the X. Actually, we don't really need the norms of the X to compute nearest neighbor search. And then realize that computing all the dot products between the Xi's and the Yj's exactly corresponds to making a matrix multiplications between the matrix X and the transpose of the matrix Y. Okay, so X is an MD array, Y transpose is a DN array, and so X at means just matrix multiply, X at Y point C is going to give you all the dot products between the Xi's and the Yj's. And the good thing is that this operation was provided to you by NVIDIA, essentially through the cuBLAS library, and it's going to be way more effective than what we did here. It's going to be way more effective than allocating an MND array and then performing a sum. Okay, so this is just already one simple trick that I didn't know, when I started my PhD. So just by doing that already, you're going to win at least an order of magnitude in terms of speed. Just by understanding that using as many operations that are provided to you by NVIDIA is the way to go. Okay, so then here I'm just computing the dot products, then I'm computing the squared Euclidean norms of the Y's, and then I'm essentially approximating my square distances using this formula. I don't need this term because it's constant on the rows of the distance matrix, and then I compute the square distance. So now, what is a bottleneck? Yes? So do you explain why the dot product is much more efficient than making the pairwise is fundamental? Yes. Okay. So I'm going to show you a diagram in the next slide. But it's a good question. Okay. The thing is that to compute the dot product, this program, so the mathml that is provided by cuBLAS, doesn't need to allocate an M and D array. Actually, the cuBLAS program first it allocates an MN array. So if D is like equal to 100, you already win a factor of 100 in terms of memory footprint on your device. And then the idea is that this program is going to compute the summation over the dimensions of F, over the dimensions D, of the D features on the fly. You do not need to store this result. What's going to happen is that the program is going to have in the thread memory is going to have xi, and then it's going to load. It's just going okay. It's going to be a bit more clear in the next slide, but you can optimize the memory reads. You can optimize the number of times you read the YJs by relying on the shared memory. And so you drastically reduce the number of times you access the data, and at least you can understand, without looking at the code, that you're going to save a lot of times at the moment when you write the data, because this program is never going to want to write into an M and D array. It's only going to want to write in an MN array. So this is clear. Why you can also save time at read time is much less clear. You have to look at the code, but okay, you can do it. Yes.
And what do you say that we have a MND GPU computation only if D is greater than 100?
Yes. Okay. So it's just that here it's about the bottleneck. So if D is larger than 100, so okay, just to say that in this program, by far the most expensive line of code is this one. And basically this matrix multiplications makes on the order of M times N memory transfers, at least at write time, and M times N times D computations, multiplies and add. And the thing is that I told you that a memory access costs on the order of 100 arithmetic operations. So the idea is that if this number of arithmetic if the dimension is small, then making those M times N times D multiply add is cheap, and we are going to be bottlenecked by the memory accesses. Whereas if we have many dimensions, for instance, if we are doing k-nearest neighbor search on MNIST, which has 784 dimensions, then we're going to be bottlenecked by the GPU computation. Okay. Every time you're going to see a 100 in today's talk is going to be about this latency of memory accesses. Okay. So that's a third strategy. And then if you go even beyond that, you can be even more clever by using on-the-fly summation, okay, which is essentially what is being performed here, but going even further. So, because you realize that if you just want to perform a nearest neighbor search, we do not really need to store the matrix of square distances. What we can do instead is to create one thread per point xi, and then loop over all the points yj. Okay, and if you do that, you're going to pay some memory accesses whenever the thread reads the coordinates of yj. But for instance, you're never going to pay a memory write. You're never going to pay a cost for memory writes because you're not writing anything. You're just fetching information and keeping track of the current best candidate for the nearest neighbor, And then once you have gone through all the points yj, you have one integer that you write back to memory, and this is very cheap. So that's what we call an on-the-fly reduction. And out of the box, it's not very expensive. Exactly, that's what I told you. It's not clear to understand why it can go faster, because still here, if I start one thread per points xi, and that each thread has to read the points yj, I still pay n times n memory reads. But then you can be clever and use a shared memory, because you remember that our points are organized in blocks. So we can group our cores are organized in blocks. So we can group the threads together. And then the idea is that we are going to give as homework to all the threads in a single block. We are going to ask them to work on contiguous slices of the array xi. And then the idea is that we are going to loop over the points yj, but we are going to share all those memory reads by first making a memory transfer from the device RAM into the shared memory, and then during the loop making much cheaper memory transfers from the shared memory to the thread memory. And if you write the complexity, you realize by doing that, essentially, you've reduced the number of memory reads. You've divided it by the number of threads that you have in a block. And this number of threads is typically 100. So you have reduced the effective cost of memory accesses to that of an arithmetic operations. And so by using this optimal memory management strategy, you retrieve the expected bottleneck of m times n times d arithmetic operations, which is so that's fairly advanced, but this is what we call a tiled reduction schemes, because we have taken this distance matrix and processed it tile by tile. And the matrix multiply in cuBLAS works a little bit like this. So what can you take back from this fairly in-depth explanation? Well, first, you realize that just to compute this very simple operation, okay, like for all index I compute the argmin over the indices j of this sum over the d features of xik minus yjk. Well, you see that by being clever, you can produce improvements by orders of magnitude. Okay, every step, basically every slide here corresponds to a speed up by a factor of 10 or 100. Going even further, if you're working with structured data, you can try to leverage your structure to speed things up even further. Okay, it's typically something that you do in 3D, but that you can also do for very large data sets that are not random. The idea is that, to perform nearest neighbor search, you're just interested in points that are in your rough neighborhood. You don't have to perform queries, nearest neighbor queries with all the points in the data set. So what you can do is you clusterize your 2-point clouds to have rough regions, know that, okay, some points are more on the right, some points are more on the left. Then you have to sort your 2-point clouds to ensure that your clusters are stored contiguously in memory. And then once you have done that, it's possible to take this scheme and to skip whole blocks in the computation, basically because you say, okay, if the cluster centroids are too far away from each other, you know that you're not going to find good candidates by performing the pairwise computations. So this is more like a mathematical trick that relies on the structure of your data. And to tell you that this type of algorithm, it's very standard. It's extremely useful for data science in general. So you have high quality benchmarks on annbenchmarks.com. You have very high quality libraries. So I think the standard library in the field is called FICE. So it's written by people who are at INRIA, 5-7 years ago, but then they went to work at Facebook, like in Paris. So FAIS, it stands for Facebook AI Similarity Search, because making a nearest neighbor computation is the same as finding the most similar vectors, and it's very useful, to decide what content you're going to show to users, etc. So just to show you that, okay, if you want to get optimal performance, you can try to be clever. So now we're going to spend maybe 1 hour to talk about kind of what's new. Like, where is the field heading to? So the first major aspect is everything that's related to compilation. Compilation, I don't know, out of curiosity, like, do you know what this means? Oh, not really. Okay, so that's good. You know, it's very important to understand that the guys who develop compilers are the people who allow us to work, actually. So compilation is the task of turning high-level code into assembly or binary code that's going to be very efficient. You know, back in the days, in the 1950s, people were directly writing assembly, so they had to be very clever, etc. And then progressively, as computers became more and more powerful, people started to use high-level languages. And then obviously, computers do not understand high-level languages. So you need to have a translation between the two, and this is a compiler. Now, what we've seen already is that if we just look at one of the most simple scientific programs out there, it's already very hard, okay? Because you have so many different strategies. Like we have seen already 4 or 5 different strategies to compute a nearest neighbor query that are increasingly fast, but complex. And what I haven't told you is that if the number of query points, like M, is like smaller than the number of cores, you need to do completely different schemes to be optimal. Like, for instance, having a data set and saying, I want to find the nearest neighbor of 1 point, completely different CUDA program. So super large field of space of programs. And the thing is that basically out of the box, a naive GPU implementation that you would write by hand as a first draft, or that a suboptimal compiler would produce out of your Python program, it's often going to be 2 or 3 orders of magnitude too slow. And so it's very annoying because it means that reaching optimal runtimes is hard. So it means that people are kind of guided towards a few operations for which people have developed optimal binaries. And so it constrains research. So this problem, just to tell you, it's not just any computer science program, you know, it's not easy, it's very deep. So for instance, it's extremely related to the coloring, to the graph coloring problem. Okay, maybe you've heard about the 4-color theorem. It's something people talked about it, especially like 10-15 years ago. It's one of the first theorems that was proved using computers, you know, automatic verification tools. And basically, this theorem tells you that if you take a map, so here it's kind of a stylized diagram of like France, the UK, Spain, Germany. If you take this kind of map, then you can color the sea in blue. And then you can use only 3 colors for all the continental countries. And what you can guarantee is that there's a way of coloring the countries such that any 2 countries that are connected to each other by a frontier, by a segment, are going to have different colors. So the statement is that if you take a graph that can be embedded on the plane, so a planar graph, then there is a way of assigning colors to the nodes such that 2 nodes that are connected by an edge have a different color. So that's the representation. And so okay, it's well known that okay, it's a hard mathematical statement, etc. And actually, one of the main applications of this field of research is compiler theory. And why is that so? That's because let's look at a typical computer program like a function f that takes as input a float number a, and then creates a variable b which is equal to a squared, then a variable c which is equal to 5 times b, a variable d which is equal to c plus 6, and then returns d. Out of the box, the programmer, the scientist, used 4 different variables to perform these computations. And maybe that's important because in the code, maybe it's a physical simulation, it's a physics simulation code. All those different variables, it's an energy, it's a velocity, they have different names. But what we've seen is that the actual hardware may not have enough storage space close to the compute units to store all those different variables. So what may happen, for instance, in a very low-end CPU or GPU, is that you only have enough room for 2 independent variables. Okay, so in practice, it's more that instead of having 4 variables in the code and 2 variables in the hardware, like we have several thousand variables in the code, and as you've seen, we only have storage space for 100 variables. So the compiler has to make code optimization to reuse physical storage space for different variables. And the way programs do this is by making first a static analysis of your code. So what they do is they create a graph where every node is a variable. And then basically the code looks at all the lines of the program and is going to create an edge between 2 different nodes whenever it understands that 2 different variables have to be alive at the same time. So for instance, here, just looking at this line, we see that A and B cannot be stored at the same location, okay? Because A and B are alive concurrently. Likewise, C and B are alive at the same time, and D and C are alive at the same time. So here, in this very simple program, you have this graph with 4 nodes and 3 edges. And then, using a combinatorial optimization routine, you can color this graph using 2 registers, using 2 colors. Okay? Because you say that A and C are never alive together, and B and D are never alive together. And so it means that in your assembly code, in the binary code, we can replace all references to A by an explicit reference to a physical register, like a physical location in the thread memory, which is called R1. And all references to B and D will be replaced by a reference to a second register, R2. Okay, so like being able to color a graph with 100 colors is very important, because if you're able to do it, then you're able to fit your program in the thread memory or in the shared memory, so it's going to be fast. And if you cannot k-color this interference graph efficiently enough, then the compiler is going to say, okay, we are going to have to swap. We are going to need to store intermediate results in the big device memory, and so it's going to be way, way, way slower. Okay, it's exactly what happens on your computer when you fill your RAM. When you fill your RAM, essentially the computer decides to use your hard drive as a swap space for RAM. Here it's a bit the same thing. If your registers overflow, we say that there is register spilling, and we have to swap in the RAM, and basically it's game over. So what happens in practice is that compilers scale up to a certain type of graph, and then we always use programs that fit within registers memory. Otherwise, we observe that they are too slow. So, okay, just to tell you that in compilers, you have very deep math, and obviously, it's very, very hard to develop a state-of-the-art compiler. So for a long time, compilers were kind of tied to a language and a binary language. Basically, compilers are translators between a high-level language like Python or C and a low-level binary language like a set of instructions for CPU or GPU cores like x86, ARM, PowerPC, those kind of of things. And for a long time, it was hard to share insights and expertise between like GCC and a typical Fortran compiler, etc. But a project that really changed everything is LLVM. And LLVM is a compiling framework that is both language agnostic and hardware agnostic. So it's a way of designing compilers where first you create a language-specific front end that translate the C code or the Fortran code or the ADA code into what's called an intermediate representation. Then LLVM optimizes this intermediate representation and then performs hardware-specific optimizations at the end to produce binary code, which is going to run on x86 cores or ARM codes, etc. Okay, and so this project, I think it's like 90 years old now, but it really gained up traction over the last decade. It really consolidated the field for the greater good. Like compilers today are way more efficient and way faster than they were 10 years ago, for instance. So, and that's massive game changer for us because it enables what's called just-in-time compilation. Maybe you've heard about it. Like if you ever used PyTorch, you know you have PyTorch.jit. And you know that it's supposed to accelerate your code. Well, JIT stands for just-in-time compilation. The dream that's behind this acronym is that we'd like to be able to turn high-level Python code into an optimal GPU binary on the fly. Okay, so that's the end target for compiler theory. The reality is that it's very, very hard. Okay, it's a hardcore combinatorial problem with strange constraints that come from the hardware, from design choices. So in practice, if you want to be optimal at a given task, you have to specialize. So all those compilers need to rely on task-specific heuristics to be really competitive in their given niche. So you have many libraries that promise just-in-time compilation of scientific code, but if you really test them out, you realize that they focus on different targets. So historically, the first community that used this just-in-time compilation framework is, as always, a gaming community. Basically, the people who develop rendering code. And so in this field, just-in-time compilation is known as shader compilation because basically the programmers were writing a small snippet of code that explains how we should compute the shade of a given triangle given some illumination conditions. And then it was compiled, so a very short bit of C++ that was then compiled into binary code and done in real time. So typically, in the loading screensaver, in the loading screens that we are seeing at the start of video games 10 years ago, part of this time was taken up by the compilation of shaders. Okay, so that's important. But then, okay, progressively, people started to use this framework, as it became more and more mature. First, for optimized convolutions on 2D and 3D grids. And here, there's a lot of margin of improvement because, out of the box, maybe 10 years ago, NVIDIA was giving to the community one binary for convolutions on 2D images, through the CUDA library. And then people realized that making a convolutions with 3x3 filters and 64 channels is not exactly the same thing as making a convolutions with 5x5 filters and 32 channels. It's different integers parameters that should be mapped differently to the actual hardware structure that we have. Okay, and so this is why you have several language-specific or optimization, for instance, within TensorFlow and PyTorch, that target this problem, and that's very hard. You have loads of very clever people focusing only on this. Okay, and then perhaps most recently, something that became integrated within PyTorch and within TensorFlow is a fusion of matrix multiplications and nonlinearities like ReLU, rectified linear unit, these kind of things, for multi-layer perceptrons and transformers. Okay, so this is what's called operator fusion. So obviously, just-in-time compilation in general, it's operator fusion. But what kind of operator fusion are optimized well enough? Well, it's up to the developers of the library. Skilled CUDA developers are very expensive. So in practice, you just target what is critical to your business, right? And you leave the rest to the community. So basically, as you see, a critical mass, a critical scientific mass is required to attract investments. So gaming, convolutional neural networks, transformers, definitely there's enough interest in the industry to motivate this. But what about everything we talked about? Okay, what about geometric machine learning? So maybe a bit of context is that geometric machine learning, primarily it's done by like mathematicians or engineers, but like from mechanical engineering, etc. So we like to represent most objects as tensors. Okay, and it's a trend that has been going on since Fortran. If you look at Fortran, it was one of the first programming languages with explicit type for arrays, explicit instructions for matrix multiplies. Then you had MATLAB, NumPy, PyTorch, TensorFlow. It's in the name. And the problem is that due to everything I showed you so far, the fact that on the GPU, the bottlenecks come from constrained memory accesses, working with arrays is not that easy. Okay, first, because all those long access times between the device RAM, the GPU RAM, and the cores and the registers penalize the use of very large, dense arrays. Okay, that's what I showed you. Okay. This program was kind of clever, but not as efficient as something online, where we never instantiated the distance matrix in memory. So this means that maybe understanding distance matrices as real arrays is not so clever for geometry. The second thing is that, okay, a common workaround is to say we're going to use sparse matrices, okay, matrices that have few non-zero coefficients. But then what I told you, the fact that GPUs are hardwired to perform contiguous memory accesses penalizes the use of sparse matrices. Because on a GPU, it's much more efficient. Basically, if you access one coefficient, you get access to the whole row of your matrix for free. So making those random accesses, using a list of edges, etc., it's going to be like 2 orders of magnitude slower than it should. And so it means that in practice, if you try to use sparse matrices with PyTorch, you're only going to see a speed up if your matrix has like less than 1% non-zero coefficients. So it's fine if you're working with some types of graphs, but for everything else, it's too restrictive. So this means that in geometric machine learning, when people want to reach optimal runtimes, they have to make a choice. So either you restrict yourself to the operations that are already well supported by NVIDIA. So convolutions on images, fast Fourier transforms, matrix multiplies. Or you can decide to invest 6 months of your life into developing new routines from scratch in C++ and CUDA. And when people do that, usually it's extremely well received by the community. Like, for instance, those are 2 projects that correspond to papers that I gave, in the list of projects that are like thousands of citations, like FICE or KPCon. Essentially, the main contributions of those papers is that the authors spent 6 months or a year developing a CUDA kernel to implement a point convolution layer or something. So that's fine, but it really goes against the ethos of all this deep learning literature, is that we like the modeling freedom that is provided to us by automatic differentiation, etc. So seeing the situation, with 2 colleagues, Benjamin Charlier from Montpellier and Joanne Glonès from the University of Paris, we decided to kind of do this job of designing an optimal CUDA scheme for geometric operations once and for all for the community, and then package it for everyone. So we develop and still maintain a library, KeOps, for kernel operations.io, which is with a website that provides efficient support for symbolic matrices. And by symbolic matrices, I mean all the arrays that you may understand symbolically as large matrices, but that really come from a relatively small formula that you evaluate on data arrays. So for instance, a squared Euclidean, a matrix of distances. Okay, a matrix of distances comes from a formula F, which is a squared Euclidean norm that is evaluated on points xi and yj. Okay, and this is what gives you the coefficients at location ij. You have all the kernel matrices that we talked about. They clearly fall into this category, and numerous transforms like a non-uniform fast-forward transform, a functional transform. You're going to be able to express them in this framework. Okay, and the idea of KeOps is that we're going to leverage this computational structure to speed things up by implementing those kind of optimal schemes, those optimal schemes instead of those ones. Okay. So in practice, okay, KeOps, it's packaged as an extension for PyTorch, NumPy, MATLAB, and R, both on CPU and GPU, fully supports automatic differentiation. And under the hood, basically every time you call a reduction, like a sum or an argmin on a symbolic matrix, you trigger the just-in-time compilation of an optimized C++ scheme. Okay, and so basically PyTorch generates an optimized C++ code, and then we rely on LLVM and the CUDA compiler to turn it into a binary. So it's like a two-step compilation. And the orders of magnitude that you should have in mind is that if the formula F is simple, and by simple I mean less than 100 arithmetic operations, you should be able to work with a matrix that has 100,000 rows and 100,000 columns in 10 to 100 milliseconds, and a matrix that has 1 million rows and 1 million columns in 1 to 10 seconds. Okay, so, and it's not unexpected, because when you buy a GPU, NVIDIA tells you that you're buying 1,000 cores. One core is like a gigahertz, like a billion operations per second. So you're buying 1,000 billions operations per second, a teraflop. And a matrix that has 1 million rows and 1 million columns has exactly 1,000 billions coefficients. So that's the orders of magnitude that you expect. And so with KeOps, for formulas that are simple enough, you reach this hardware ceiling. And that's typically 1 or 2 orders of magnitude faster than what people were used to due to PyTorch, etc., on a wide range of problems. Yes.
But then you store the matrix in memory?
No. So you don't store it. Yeah. So basically, it's only useful, for instance, if you want to perform a nearest neighbor search, you do not really need the matrix. Or if you want to perform a Gaussian process regression or a kernel interpolation or even a transformer attention layer, you do not really need to store in memory this matrix. So you can compute things on the fly. So it's important to understand that most matrices that we manipulate in applied math have this structure. And that's very different to what people are doing, for instance, in natural language processing. For natural language models, the models actually need large matrices that act, that act as dictionaries to encode all the semantic embeddings. So people who do MLPs, they are actually interested in genuine matrix multiplies. But if you do geometry, actually, we are not in this regime. So our matrices have a more mathematical or algorithmic structure that we can leverage now with KeOps. And KeOps, it's only possible thanks to LLVM. Basically 10 years ago, it was impossible to try to build this project. 5 years ago, when we started in 2017 and LLVM was not that mature, it was quite tricky, and now it's very easy. Just to tell you that it's just about bringing to applied mathematicians all the good stuff from the compiling community. So, if I show you that, just to be clear, what does it look like in a code? Well, I come back to this nearest neighbor search in dimension 50. that we discussed earlier. So now I create my point clouds with like 1 million rows for the xi's, 1 million rows for the yj's, and 50 columns. And I send them on the GPU using this CUDA instruction. Then the only time where the code sees the KeOps library is when I wrap my dense arrays into the lazy tensor object. So I turn dense arrays into symbolic matrices. Exactly like, it's the same kind of operation that you would use to turn a dense array into a sparse matrix. So here I write that xi is equal to a lazy representation of x, yj is a lazy representation of y. Then, now that the library understands that this is a symbolic object, we can use standard mathematical operations and write that, okay, the matrix of squared Euclidean distances is just xi minus yj squared. And I make the sum with respect to the dimension of size 50 here. I get an object with like 1 million rows, 1 million columns, but symbolic. Otherwise, I would get an out-of-memory error. And then the idea is that when I call a reduction on this symbolic object, this triggers the just-in-time compilation of a very efficient nearest neighbor query. And so here I recover a standard PyTorch tensor. So,
and do you have an approximation when converting into a lazy tensor, or is it an exact conversion?
No, it's an exact conversion. So, and the idea is that, okay, the KeOps library, it's all about allowing researchers to study other things than just Euclidean metrics. So the script of this previous slide, it's basically as fast as it gets for brute force nearest neighbor search. So it's on par, sometimes faster, sometimes a bit slower than the brute force CUDA scheme that is provided by this reference FICE library. And the good thing is that we can use it with any metric, because it's not a static binary. So if I want to use a Euclidean metric, I use xi minus xj squared. But if I want to use an L1 Manhattan metric, I can write xi minus xj, I take the absolute value, and then I take the sum. If I want to work with a cosine similarity metric, I can use a dot product. And if I want to work with a Poincaré metric on the hyperbolic half plane, I can also use it using this formula, which is essentially equivalent to the hyperbolic metric. So, okay, the good thing is that this KeOps library, so it's really meant for research, so it supports arbitrary formulas and variables. So we have lots of reductions, like k-mean, matrix vector products, logsum exps, lots of operations. So you can use mathematical things, but also small neural networks. It counts as a small formula. And advanced schemes, like you can do batch processing with heterogeneous batches if you want. You can do all those sparsity approximation strategies. You can implement them fairly easily. And it's fully compatible with PyTorch as far as automatic differentiation is concerned. And in terms of runtimes, okay, the main point of the library is that it allows people to work with millions of points at a time. Realize that in 2022, a million of points is really not so much. And it's important because I think most people, especially on the mathematical side, believe that 10,000 points, it's already a lot. It was a lot 10, 15 years ago, but GPUs have really made constant progress, so we can use that. So here, I'm showing you a benchmark of a Gaussian convolution between two clouds of n 3D points, okay, on a typical gaming GPU. So here, I generate two arrays of shape n times 3, n times 3. Then I compute a symbolic matrix, kernel matrix, where the coefficients at location ij is given by a Gaussian kernel. It's evaluated between xi and yj. And then I use this matrix to perform a matrix vector multiply. So that's the fundamental operation in many applied fields. And I show you a benchmark where the number of points ranges from 100 to 1 million. And with runtime that range from a fraction of a millisecond to 10 seconds. Okay, so the first implementation is what you get with NumPy on CPU. So you get this kind of curve. Okay, so first you notice that everything here is brute force. We're not making any approximation out of the box. So whenever I multiply the number of points by 10, I multiply run times by 100. So in log scale, it means one cell to the right equals two cells up. So that's quadratic runtime. And on the CPU, basically, okay, for 1,000 points, it's fine. For 10,000 points, you're already starting to wait. So the whole point of GPUs is that you can implement the same scheme using PyTorch. Using your 1,000 cores that are provided by your GPU. And so you get the same behavior, but with a much better constant. Okay, so like typically a speed up by 300. So that's already great. And it means that with PyTorch on a GPU, you can already work with clouds of like 2,000 points very efficiently. And that's why in computer vision, people, like all those standard benchmarks from 5 years ago, the shapes are always subsampled to have like 2,000 points. It's because it is what fits on a GPU with PyTorch. And large-scale point clouds require handcrafted routines. So that's the typical runtime. But if you go beyond like 50,000 points, your GPU cannot allocate in memory a large array like with 50,000 rows, 50,000 columns, so you get an out-of-memory error. And so that was the main motivation to develop KeOps. So initially it was just to solve this out-of-memory issue, perform the computation on the fly. But then when we actually implemented it and made tests, we realized that it was also out of the box, typically an order of magnitude faster than PyTorch for those kinds of computations. So this is typical runtime. You see that for a matrix that has 1 million rows and 1 million columns, you work in 1 second. So, and out of the box, okay, you can implement approximation schemes, like Joan Glones, is still publishing papers on that, and we are going to integrate some of the schemes in the main library. But out of the box, it's quadratic. Okay, all those curves have the same slope, but the constant makes all the difference. So that's the runtimes. And maybe one last remark is that you see that runtimes never go below 1/10 of a millisecond, and that's because that this is the time it takes to wake up your GPU. So if you want to be more efficient, well, if you only have one shape, you cannot. If you have one point cloud, you cannot be more efficient than that. But if you're doing training, for instance, you can work with batches of point clouds. And if you do that, it's totally doable, both with PyTorch and with KeOps. You're going to recover performance curves per shape, which are fully linear. Okay, so just to give you it's kind of the current state of the art as of today. So 10,000 points, it's really small. And basically, if you have less than 1 million points, you can go brute force. You can very much decide to be clever, but it's only going to be useful to go beyond that. So as you can imagine, this library is a very good fit for machine learning research because it means that you can implement things like k-means or Gaussian mixtures with any kernel, metric, or formula that you like. So, I presented to you a lecture on hyperbolic geometry. That was one of the main motivations. Allow people to work with like L1 Euclidean geometry, L1 Manhattan or point carré métrique, without having to lose too much on the computational side. Because that was really the situation 5 years ago. You really had this image that people were constrained to walk on a very tight mountain path of what was supported by PyTorch and TensorFlow. And every time you wanted to step outside of this, you pay the price of like a slowdown by 2 orders of magnitude. And I think it was really making the literature kind of more and more redundant, less interesting. And so the whole motivation was to allow people to pick models, not just because they are supported by PyTorch, but because they are actually relevant. Okay. Also, just use the fact that GPUs are not just matrix multiplication units. It's much more versatile than that. It was designed to simulate physics in 3D. So the space of programs that can be accelerated by GPUs is much wider than convolutional neural networks. So beyond, if you want, you can do spectral analysis, you can do UMAP. And maybe the core applications historically is everything that's related to kernel methods, like kriging, Gaussian process, kernel regression. That's why we call the library KeOps, because it was really the first market, if you want. So I already talked about this a little bit. Kernel regression is what's behind all those curves, where you have samples and you want to find a fitting curve and you want to get confidence intervals outside of your sampling data set. And what we've seen in lecture 2 is that under the hood, those methods just rely on the resolution of a linear system where the matrix that you want to invert is a kernel matrix. So we've made everything that was needed to ensure that those KeOps symbolic tensors could be interfaced with the standard solvers in the field, like SciPy, or the solvers of GPyTorch. And so, for instance, I didn't do it, but the colleagues who developed GPyTorch, which is one of the main libraries for Gaussian process regressions, basically they used KeOps. They just added a KeOps backend to their library, and suddenly it allowed them to scale things up much more efficiently than what they were used to. Okay, so on a typical data set with like 300,000 rows and 3 columns, typically something for 3 division. Well, a Gaussian process regression that was taking 7 hours to be trained with 8 GPUs suddenly could be trained in 15 minutes on 1 GPU. Okay, and going further, of course, the idea here is not that using optimal implementations is in conflict with being clever. The idea really is that those two things are orthogonal components of what makes a program work. And so it's very much possible to use those kind of optimal binaries with optimal statistical routines. And so now, so KeOps, it provides a fast backend for research codes. And so over the last, basically between 2017 and 2020, the field of kernel regression went from training models with 1 million points. So in 2017, training a Gaussian process regression with 1 million points was considered a performance. 3 years later, it was 1 billion. Okay, and that was because of this combination of great progress on the theoretical side and those optimized binaries, so that people were not aware of. So going further, for me, the motivation is that this kind of tools, you allow researchers to focus on models, results, and theorems. I told you in the first lecture, the main point of doing math is to be creative. I think it's less about providing optimal performance and more about understanding what you're doing. So, for instance, I'm very happy to have friends like Antoine Diez or Grégoire Clarté who could use those libraries to simulate like flyers or spermatozoids, hundreds of thousands of swimmers. And so to scale up their numerical simulations of like mean field games, packing problems or Monte Carlo sampling. So that's pretty happy about that. And in my own work, okay, I already showed you that I worked a lot on speeding up things in geometric deep learning or optimal transport theory, and obviously all of that was because we made the effort as a team to create this KeOps library. So if I had to make a recap on compilation, well, I have 3 main messages. The first one is that turning scientific code into optimal binaries is very much an open problem. So as of today, there is massive room for improvement on the software side. Usually, if you go in a new community, and basically, if there is no one in the community who has spent time thinking about that, chances are that it's possible to speed things up by 1 or 2 orders of magnitude. Currently, like last year, I did just that for the community of survival analysis, like creating new packages that are going to be released soon that implement the standard models in survival analysis, like the Cox proportional hazards model, but like 1,000 times faster than what people use. So, just a message that it's not for everyone. I'm sure that some of you really think that, okay, this class is way too technical, we don't care about C++, but if you like programming, I can tell you that I think it's a very valuable and impactful skill. Like all those libraries that we developed, so far they've been downloaded like 250,000 times, just for small software that we developed at 3. Definitely, probably if I hadn't done that, I wouldn't have got my job at INRIA. And actually, I made a very conscious decision during my PhD to focus on this instead of focusing on proofs, because I thought, maybe I'm going to go in the industry. Probably in the industry, they would prefer someone who's able to code instead of someone who's able to make proof that no one really understands. So just to tell you, even if it's the MVA, the Master of Mathematics, software engineering is a massive part of this field. So it's good to be at least aware of it. The second message is that symbolic matrices, they are really are to geometric machine learning what sparse matrices are to graph processing. So it's an idea that's pretty old, but that has only become effective thanks to LLVM, thanks to the progresses in compilers. 10 years ago, it was impossible to implement KeOps. But now it's possible. And so with KeOps, which is really meant for researchers, you get a free speed up for a wide class of problems against PyTorch, TensorFlow, and JAX. And the idea really is that all those tools like GPUs, software, they are here to open new paths for geometers and statisticians. So like young, probably PhD students next year. So GPUs are way more versatile than people think, probably than your advisors are going to think. And so there's ongoing work worldwide to provide fast GPU backends to researchers, going beyond what Google and Facebook are ready to pay for. So we talked quite a bit about PyTorch geometric. PyTorch geometric is exactly that. Basically, the main guy, Matthias Fey, who developed PyTorch geometric, one of his main contributions was just implementing binaries like CUDA C++5 that were turned into binaries for graph convolutions that were way more efficient than what you could do using PyTorch. And that's the core of his library. Then he made a great work on the documentation, on the packaging and everything. And it has really been a game changer for the field. Just to tell you that research teams in academia are working on this worldwide. So that was for the software side. And now to conclude, maybe in like, I'll go quite fast, I think, on the hardware progresses, like optimized AI calls. So, maybe let's look at the current AI architecture. Like as of today, we're in 2022. The flagship AI chip is the NVIDIA A100 GPU. I don't know if you've ever bought that, but before it was the V100, before that it was the P100, but today it's the A100. And the great thing is that the architecture of the A100 is fully documented. So you can go, it's a blog post by NVIDIA researchers where they really dive into those diagrams and explain to you everything that there is to understand as a user. So here it's a diagram for the G800 architecture where you have 128 blocks fully working. Okay, and as I told you, in practice, typically you do not buy a perfect G800. You buy a slightly defective A100 GPU where you have like more 108 functional blocks out of 128. That's what you buy. And so basically here you have tons of redundant blocks that are the physical CUDA blocks that I talked about before and which are called streaming multiprocessors. And if you look at the diagram of a streaming multiprocessor, first, here you have the shared memory. So this is really like the office shelf, in the photo that I showed you earlier. And on the Ampere, so on the A100 GPU, it's a bit less than 200 kilobytes of shared memory. And then the team, so the block is split in 4 squads. So kind of 4 tables in my office. And those squads are like unified physical threads that are called warps in the CUDA documentation. And each of those comes with some stuff, some weapons to tackle our computational problems. So first, you have thread memory. So that's those register files. That's around 64 kilobytes of thread memory per team. And then if you zoom in, you have 16 cores that are dedicated to manipulation of int32 numbers, 16 cores that are related to the manipulation of float32 numbers, 8 cores that are related to the manipulation of float64, and 1 tensor core. And what I want you to understand is that the first 2 types of cores are like the legacy, the historic types of cores that were present in the very first GPUs. And the float64 and tensor cores are kind of novel additions to this to our hardware environment. So what are they? Just maybe you don't know how numbers are represented in memory. Okay, you know that we are just manipulating bits, zeros and ones, and so you have conventions on how to interpret those bits as integer or real numbers. So the first convention is just int32. So you have a stack of 32 consecutive contiguous bytes. Basically, the first byte is a bit like a sign. And then you have 31 significant digits or bits, like digits in base 2. And so here there's a typo, there should be a plus. This allows you to represent numbers between -2 billions and +2 billions. So, and if you're working with a computer, you absolutely need to have dedicated units to manipulate those numbers, because you're going to need them to perform all the required computations on memory addresses. You know, like if you want to loop over an array, you're going to have to say, okay, an array, at which address should I fetch memory next? And for this, you need to make all those algebraic arithmetic computations on integers. And so basically those 16 int32 cores that you see here, you can understand them as physical pieces of hardware, like transistors, logical gates, with dedicated circuits that perform, for instance, these fuse, multiply, add operations, where you take as input one int32, a second int32, a third int32, and you compute A times B plus C, and you store the result in a new int32 buffer. And that's very typical. So that's fine, but obviously you cannot really do continuous mathematics with integer numbers. So instead, what we typically use is another convention, which is called the float32 convention. So here, the idea is that we understand this sequence of bytes, of bits, the sequence of 0 and 1s, as a scientific notation for your number in base 2. So the first bit is a bit of sign. Then you have 8 bits for the exponent. And then you have 23 significant digits in base 2. And the idea, so you have some subtlety, because you also need some values are stored to represent plus infinity, minus infinity, and not a number. So it's not as simple as it looks. But on the whole, using this scientific notation, you're able to represent magnitudes of numbers between 10 at the power minus 38 and 10 at the power plus 38. So for instance, you're never going to be able to represent 10 at the power minus 40 using a float32 number. Or actually you could, but 10 at the power minus 100, let's say. This you cannot do. And then your 23 significant bits are kind of equivalent to 7 significant digits. Okay, and the idea is that, why are those two conventions the favorite ones, for GPUs? Well, that's because you need those ones if you want to loop over your arrays. And 7 significant digits, it's good enough for 3D gaming. Okay, that's the kind of precision you need if you want to implement the Quake engine or the Unreal engine, this kind of thing. So that's fine. And so those were the first generations of GPU. But then the people at NVIDIA understood that if they invested enough, there could be a market in scientific computing for GPUs. But they also quickly realized that if you show this to a physicist, he's going to scream. Okay, like you want more significant digits to perform physics computations. And so this is why they added float64 cores that are optimized for a different representation of float numbers, a representation where you have 1 bit of sign, 11 bits of exponent, and 52 bits of significant digits. And those 52 bits of significant digits kind of correspond to 16, 17 real digits. And this is good enough to represent physical constants, so that's fine. Okay, so actually they opened up a new market by allocating silicon real estate to float 64 computations. So, and that was the state of the art maybe 5 years ago. But then NVIDIA also understood that people were starting to make lots of matrix multiplies without caring too much about numerical precision, right? If you're just training a neural network, you don't really care about 7 significant digits. It's all noise anyway. And definitely you don't care about 16 digits if you're implementing a convolutional neural network or a transformer. And so they decided to add support for new types of float numbers, such as the bfloat 16 convention, which is like half of a float 32 number, where you have 1 bit of sign, 8 bits of exponent, and 7 significant bits. And those 7 significant bits are kind of equivalent to 2 or 3 significant digits. So it's garbage to make math, it's garbage to make physics, but it's good enough to do deep learning, because you just care about the orders of magnitude of your coefficients. You don't care that much about their precise value. So it's good because it allows you to pack twice as much information using the same cost in terms of memory transfer, which is great. And then you can also realize that if you take a block of 256 contiguous bits, okay, typical, like you can think of it as a page, as a sheet of paper on the draft table of a worker, those 256 bits, you can use them to represent 16 numbers encoded as bfloat 16. So you can understand this page as a 4x4 matrix filled with bfloat 16 numbers. And so realizing that, they decided, like the people at NVIDIA decided to add new chips, new circuits that have to be used by all the cores in the same squad together, but that perform a matrix multiplications with those kind of low resolution matrices in 1 unit of time. Okay, so that's why currently those chips started to arrive like 3 years ago, essentially with a V100 GPU. Like it's when you could start to use it as a researcher. Now they are becoming more and more common with the current generation, and they are going to be in all GPUs going forward. But you can really see this hardware innovation as a way of making matrix multiply a unit operation. And obviously, this means that implementing transformers or convolutional neural networks is kind of faster than ever. So generally speaking, today I focused exclusively on NVIDIA because this is what we use for research, in academic research. But hardware design is a fascinating field where you have many different trade-offs. In practice, when you design a chip, you have to factor in speed, power consumption, versatility, and manufacturing costs. So, for instance, I really suggest you to look at this video by Branch Education about smartphone chips. How do smartphone CPUs work? And the thing with smartphone CPUs is that you want to optimize battery life, because this is a current bottleneck for mobile devices. And so since you want to prioritize battery life, and you expect that most users are just going to use their smartphone to go on the internet and watch some YouTube videos, you can specialize. You can decide to essentially trade versatility for power consumption. And so if you look at a CPU chip in practice, you have dedicated circuits, for instance, for JPEG, or dedicated circuits for the decoding of YouTube videos in the mainstream codec. I think it's like H.264. And so the idea is that this hardware can only do one thing, but it does it very well. So that's pretty different to what we do with GPUs. GPUs are very versatile, but they have very large memory very large energy consumption. Maybe something you've also heard about is like tensor processing units, which are chips that are developed by Google. Essentially, those chips are meant to be used with transformers and CNNs, but it's perfect fit for transformers. The idea is that you can essentially only do matrix multiplies with real matrices, but you do that very efficiently and with a very low energy consumption. So for Google, it made sense to invest in this hardware. So all of this to say that hardware design is hard, and I don't know if you can really make predictions, but I think it's important to understand where the current ecosystem comes from and what are the plausible outcomes, I think, for the next few years. So the first remark is that the CPU versus GPU discussions, this uncoupling in terms of performance, it occurred when we were children. It occurred in the early 2000s, and I think it's something that we could all notice, at least implicitly. I don't know if you were already paying attention, but I was born in like 1994, and when I was very young, CPUs were still noticeably becoming better and better, and you could see it on Windows. Essentially, you could see that Windows 95 was way cooler than Windows 1, then Windows XP, then Windows Vista, and then it kind of plateaued. Like if you look at Windows 10 today or Windows 11, I don't know, it looks the same as Windows Vista. It's just a different style, but nothing has really changed. You get the impression that over the last 15 years, the laptop and desktop space matured and reached a plateau. And that's a situation which is totally different to what we see in video games. Okay, like over the last 30 years, we've gone from 2D sprites to very polygonal Nintendo 64 graphics, then smoother, and now like realistic or photorealistic renderings of Mario in real time. Okay, and this is really thanks to the exponential increase of computational power of GPUs. Now, that's all well and good, but what does it mean for us? Maybe I think we can draw a quick diagram for a quick curve for the computing power that has been available to ML, to machine learning researchers over the last decades. So, okay, back in 1990, everything was simple. We were just using CPUs, and every new generation of Intel CPU meant that algorithms went faster. But then 20 years ago, essentially the performance of CPU started to plateau, and GPUs were very hard to use. Like it was very, very, very intricate. You had strange constraints, like you could only make memory accesses at addresses that were equal to 0 modulo 16 or modulo 64. You have very strange constraints that are completely out of reach for most mathematicians. So for about a decade, early 2000s, people were kind of giving up on GPUs and were happy enough with CPUs. And so this is an era where you have so many math papers that were written, and kind of mathematical methods caught up with the state of the art, because on the CS side, it plateaued. So that was 10, 15 years ago. And then you had this revolution. Everyone cites the paper from 2012. But for me, it really started when people in Montreal or in Berkeley decided that GPUs were mature enough to invest in high-level automatic differentiation libraries. So you have the first generation of deep learning libraries like Theano and Caffe that allowed researchers to catch up with kind of Moore's law. So that's what happened between 2010 and 2015, 2017. So we caught up, kind of a miracle for people, because obviously if you do not understand the hardware space, you perceive this as a kind of incredible scientific revolution, whereas in some sense it was just catching up with Moore's law. And then thanks to this hype in the field and the obvious industrial applications, you have large industry players who invested in the field. Countries started to invest in like cloud solutions that allowed us to scale up from one GPU to like tens, hundreds, or thousands of GPUs. So that's what you can do now if you use like Amazon Cloud, Google Cloud, or like, I don't know if you're aware, but the French cloud, like Jean Zay, is really high quality. Like Jean Zay, you type Jean Zay user documentation, and basically, if you're doing your PhD, maybe as an M2 student, probably you are not going to get access. But if you're doing your PhD in France, definitely you can get access to it. It's a cluster which is basically you have the same funding as what people in physics have, but for AI. So you have loads of GPUs, fairly available, and it's kind of open bar more or less. So I really strongly advise you to have a look at the user documentation, because the official documentation is a bit hard to look at. But okay, just to tell you that's kind of what happened during my PhD. I did my PhD between 2016 2019. You really have this scaling up that appeared first with the second generation of deep learning libraries like TensorFlow, PyTorch, and JAX, but mostly because we started to use more and more compute power. And so basically for about a decade, you had a crazy, maybe unsustainable growth of the field, where kind of new benchmarks were attained like every 6 months. And then in 2019, obviously COVID appeared and it slowed down everything. I don't know if you're aware of this, but there really has been a crisis in terms of supply chains for GPUs. Basically, GPUs are all manufactured in Taiwan and maybe in Shenzhen, but I think the NVIDIA GPUs, it's exclusively in Taiwan. You also have fab labs in South Korea, basically 3 countries, 3 places where everything happens. And due to COVID lockdowns, there was a drought in Taiwan. I mean, lots of things. Essentially, it became impossible to buy a GPU. And so what happened is that gamers could not buy GPUs anymore. And we as researchers, we had to overpay massively. So basically, like the GPU I have in my office, I paid like 5,000 euros for it, whereas the official retail price is like 2,000 euros. So even if the hardware gets better, if it also gets twice as expensive, it doesn't change anything for us because we work with a fixed budget. We don't care about the number of GPUs. So that's what has happened over the last 3 years. And now, COVID is kind of over. Maybe even in China, they start to think that it's a bit over. And now we are really wondering about what's going to happen next. And I think for you, it's important because as you can imagine, depending on the growth of computational power, different approaches, different fields are going to be favored. Usually, I think if the computations start to plateau, you need to understand what you're doing more. Whereas if you have a meteoritic rise in terms of computational power, then focusing on scaling laws is where it's at. So first, I'd like to tell you that for me, it's extremely unlikely that the growth of the last decade is going to keep going for the next few years, because it was really due to the combination of catching up and then scaling things in terms of compute power. And so, okay, maybe the people at NVIDIA, Intel, TSMC, they have a miracle going for us that I'm not aware of, but if there is no miracle, it's not going to happen. So then I think you have 3 plausible scenarios. So the first base case scenario is that things go back to normal, to the pre-COVID normal. Basically that GPUs keep improving, we keep our funding that allows us to work with thousands of GPUs at a time. And so it keeps going on at a slower pace than before, but the fields keep improving. That's optimistic. And arguably, maybe it's not the most likely option because you have 2 other scenarios that are fairly plausible. The thing about the last few years is that all governments realized that we were super dependent on a few factories in Taiwan. Taiwan is close to mainland China, as you know. And I think people, basically the president of the US or people in Europe, they started to panic a little bit and realized that, okay, basically if a few factories in Taiwan get destroyed or get blockaded, we cannot build cars anymore. You know, it's not even about AI research, it's about basic utility things. So now there's a massive push, both in the US and a bit in Europe, to relocate factories. Like the US government is pouring billions of dollars of investment into this space, not to create better factories, but just to kind of copy the factories that are already in Taiwan in our countries, just in case. You know? And so, you know, if this is a trend where it's going to, well, basically we're going to prioritize energy consumption and reliability over speed. So maybe in terms of society, it's better, but as researchers, it means that it's going to stop growing. And finally, last scenario, which is also pretty plausible, is something like a war in Taiwan, or at least a blockade in Taiwan. And I say it's likely because arguably our Chinese colleagues, they're already in this scenario right now. I don't know if you're aware of this because it didn't make, it wasn't really publicized in mainstream newspapers. But in early September, the president of the United States, or the United States government, sent an order to NVIDIA and told them that they were not allowed to sell 800 GPUs to mainland China anymore. So it's an explicit blockade. Basically, they are starting to apply the same regulations to GPUs. Basically, the regulations that are applied to GPUs are starting to mimic the regulations that are applied to like defense material, like nuclear secrets, this kind of things. So there's very deliberate effort by the US government to curtail the AI industry in mainland China. And you know, in the MVA, you don't have that many Chinese students, but it's an anomaly, right? Okay, if you go abroad, you have lots of very, very good Chinese students, Chinese researchers, have tons of labs both in China, in UK, in the US, that where you have plenty Chinese people. Personally, I did 2 internships in Beijing. So, and they are a massive part of the community. And since September, they do not have access to the high-end hardware anymore. Okay, so probably the Chinese government is going to try to catch up, but currently, visibly, their industry is has like a 10-year. There's like a 10-year gap between what they can produce and what is currently produced in Taiwan. So what they are going to do, I don't know. But just to tell you that these kind of things happen, and maybe we're next. Okay, so, and if it happens, obviously it changes a lot of things. So maybe we're going to have to scavenge PlayStations. I don't know. So that's realistic. So conclusion. Well, it was kind of a fairly an overview, really. I mean, I think the whole class was meant as a geometric tour of data science. I hope you enjoyed the journey. You know, talking about manifolds, graphs, trees, curvature, and now hardware. I think, you know, my main intention when designing this class was really to broaden your perspective a little bit. You know, because maybe we can ask ourselves, what is AI research about? And probably if you ask someone on the street or if you ask someone at an undergrad level, they are going to have an outsider's perspective that resembles that of cars enthusiasts. You know, I think when people think about the car industry, I think you have lots of people who fantasize about, yeah, the different designs, different cars. You have taxis, you have trucks, you have Formula Ones, etc. And that's what you see from the outside. But from the inside, I mean, if you have like if you talk more like to professionals of an industry, you have a much more varied view. I think if you talk to people at Renault or Porsche or whatever, they're going to tell you, yeah, we do cars. But first, okay, cars are one way of going to a place or another. You also have bikes, you also have planes, you also have trains. So it's important to at least be aware that other options exist, and maybe the government is going to favor one option over the other, and it's going to destroy your career. That's likely. And also, you cannot just focus on what's visible from the outside. You also have to understand a little bit, not specialized, but just understand a little bit that engines are important, tires are important, roads are important. And just to tell you that many people, me included, we start as enthusiasts and then enter the industry to become professionals. We hope to make a career out of it for the long run. And I think it's important not to stay focused on the one aspect of an industry which is visible from the outside. Because if you have tunnel vision on a single angle, it's very high risk. It's a very high risk area. Just as an example, I think you have many people around the world who went into AI because they saw papers on GANs, 3-4 years ago. And maybe they are adamant that they want to do a PhD on GANs. But the thing is that, look, now people talk about GANs as if it was ancient history. So, if everyone goes in the same fields and if the fad switches to other subjects, then it gets complicated. So I think it's important to try to find something that really corresponds to your interests, and that's open. Maybe an analogy is that if you think of the gold rush, the famous gold rush in the 1850s, you had thousands of people trying to get rich quickly by finding a nugget, a gold nugget. But at the end of the day, the kind of lasting industrial success from this revolution is Levi-Strauss, who said, okay, I'm going to let people find gold. I'm going to sell them blue jeans, and maybe personally, my job is a little bit like that. Instead of trying to spend all of my time training deep learning models, maybe develop libraries, because then all the people who use them are going to like you, they're going to want to hire you, etc. And just a bit of advice. And you have many different ways of contributing to a field without making the high variance choices. So, the main point is that machine learning research is completely interdisciplinary. And maybe if you want to look, this is a mind map that I drew at the end of my PhD. I did my PhD on medical shape analysis, and it's something that allowed, during the 3 years, I interacted with many people, both people experts in fluid mechanics, pattern theory, statistics, optimal transport, computer vision, but also with people at Siemens, people who design MRI scans, or doctors just across the street. So that's what I appreciated most about the whole scientist's lifestyle. And maybe what I want to stress is that research is a deeply social and diverse activity, and it's something that we do not see during undergrad or during your master's. Your master's is because currently you are still spoon-fed packaged research. But probably next year, you're going to work as an engineer, or you're going to be a PhD student. You're going to quickly see this whole field from the other side of the barrier and realize that all the papers that you read have been written by actual people that you're going to meet, you're going to be friends with them, and so it's very important to acknowledge this human factor in everything we do. So, just to conclude, if I had to give you some early career advice about internships, PhDs, just because quite a few of you asked me questions, so I was thinking, okay, maybe I should give the answers to all of you at once. Okay, there are just 4 things, and then we're done. First, I think now you're probably at the stage where you're looking for an internship, looking for a PhD. Try to keep in mind that you bring much more to the table than your potential advisor. You should not see a PhD as you're going to talk to someone who's going to drip, to give you a few knowledge, and you're going to cherish it. No, not at all. Okay. The thing is that the only time in your life when you can focus full time on a subject is during your PhD. Okay, that's really what a PhD is about. 3 years when you focus on something, you become a world expert. And your PhD advisors cannot do that. First, because likely he must teach, he or she must teach, has administrative things to do, or just talks with many different people. There's a lot of networking. So very quickly, you're going to know more about your subject than your PhD advisor. Okay, so just to be clear on that. So you are the one doing the work at the end of the day, most of it. And so you have quite a lot of leverage in negotiations. As if you're able to show that you are skilled and reliable, if you can show that you're autonomous, that you can be trusted, people will really want to hire you. That's the main bottleneck in research, is finding reliable people, in a sense. So that's why I insisted on having you write project in English, etc., because it's one way just to show that at least this part of the job, you can do it, okay, make figures, etc. It's one way of demonstrating this part of your skill set. The second thing is that, in my opinion, tutoring time, like spending quality time with senior researchers and working in an open research area where you have more problems than detectives, where people are not afraid to share ideas. I think it's much more important than going in a prestigious place, okay? In my experience, really, I would advise you not to go in teams or in subfields that are too crowded, like, for instance, vanilla computer vision for automated driving. It's very interesting, of course, but you have thousands of people who want to do exactly this. And the atmosphere, people, for instance, in those fields, people fear getting scooped. Every time they submit a paper, they're afraid that 3 weeks earlier, someone already published the same idea. And you say, come on, like, you shouldn't do research just to be first. You should do research to do something new that no one has thought about. So that's the first thing. Second one is that, don't be too focused on Paris, London, Boston, San Francisco, those kind of very centralized, central, prestigious places. You only have so many researchers, PhD advisors, and to be honest, the quality of life as a researcher in Paris is much worse than what I could get in Caen, in Rennes, or whatever. So you have outstanding people, great people in those other cities, and don't hesitate to contact them. When looking for an internship, don't just ask to your MVA teachers, to your MVA professors. France or Europe or the California or the US East Coast are fairly well connected to each other. So what happens is that people work in different cities, and then every month or every 2 months, we meet each other in conferences, in workshops, so we connect. And so if you attend those events, it really doesn't make a difference to be in Paris or to be in Caen. So frankly, try to consider this. Third thing, I think you should not take for granted everything that you've seen in France, okay? Because in different countries, you will meet different people, different values, and different perspectives, okay? And what is common here is not at all common in the US, for instance. So maybe a simple question is, who is the main character of a PhD thesis? Okay, personally, I think that it should be the student, because you are the one who does most of the job. You are the one who is putting like your early career on the line, as a PhD advisor, you don't really care. So I think since you are the one at risk, you should make most of the decisions. Or basically, as an advisor, you give advice, but at the end of the day, the student should be autonomous, but be aware of the fact that in some systems, people think that it's the advisor. There is really a conception that a PhD, it's an advisor who gets money and then hires someone. It's just a delegation of workforce, but all the ideas should come from the advisor and blah, blah, blah. Okay, so just be aware of it and ask yourselves, where do you want to go? Obviously, it's always a trade-off between geography, salary, etc. But don't assume too many things. And finally, because research, it's such a social topic, I think that personal chemistry is very important. And so if you find a team in which you feel at ease in a general research area that you like, probably it's more important than the precise PhD topic, that was published, like the 2 pages PDF document, the PDF offer. Okay, you have to realize that when you write PhD thesis offers, it's kind of a baseline. We're just saying, okay, this is a subject, this is what I plan to do if everything goes according to plan. And it's here to show to the funding agencies that there is we have a B plan. Okay, it's not going to be a complete failure. At the end of the 3-4 years, the student is going to have its PhD. But usually, a nice PhD is when you start with your PhD topic and then you realize something else. You find something unexpected, which is much more exciting than the original PhD topic, and then hopefully the team says, yeah, of course, go in this direction. You know, it's a bit of a joke, but we say that a PhD that goes exactly according to plan is a bit disappointing, right? Because it means that everything was predicted 3 or 4 years in advance. So in this context, I think it's super important to always meet team members, ideally in person, but at least have real conversations with people, including the students, before signing a long-term contract, because otherwise you're going to sign for 3 years and maybe get stuck in a situation that you want to escape. Okay, and so in this context, internships, you know, it's not mandatory at all, but it's more like a trial period for you to see if the team is fine and for the team to see if you're not a total misfit. You know, like if it goes according to plan, you're going to get hired. It's more that, okay, if you really don't work, maybe things get problematic, but I think it's most useful for you as a student to see if you like the city, if you like the people, if you like the atmosphere. So that was it for the lecture. And if you only have to remember one slide, it's really try to befriend domain experts, like don't stay with your computers all the time. And when making choices, try to find your own balance.